our experiment is calibration of orifice plate. A orifice plate is a device which is generally used to measuring the flow. That means how much quantity is flowing through a duct we can directly measure with the help of a orifice plate. Basically, orifice plate is a plate with it looks like a disc, and in that disc there is a orifice. When this thin plate is placed in a duct, then this orifice plate can measure the flow quantity. Principally, let's say it's a duct having a cross-sectional area of A1, and orifice plate is put in the duct with a cross-section area of, let's say, A2. This is the cross-section area of duct A1, and orifice plate with a cross-sectional area of A2. Now, if we measure the pressure here, let's say this pressure is P1, and then after this orifice plate, let's say pressure is P2. There will be a pressure drop across this orifice plate, delta P, pressure drop across the orifice plate due to change in the cross-section area, due to change in the cross-sectional area. And if somebody measured this pressure drop across this before the orifice plate and after the orifice plate, and he can measure the flow directly. Let us see how principally how this pressure drop and flow quantity through a duct is related. If you know the Bernoulli theory, then we understand that total pressure at the point 1 and pressure after point 2 will be the same. So I can write it P1 plus half rho V1 square equal to P2 plus half rho V2 square. That is, P1 is the static pressure measured at the point 1, P2 the static pressure measured at the point 2, and V1 is the velocity at point 1, and V2 is the velocity at point 2. That means static pressure plus velocity pressure at point, that means total pressure at point 1 will be equivalent to total pressure, like static pressure plus velocity at point 2, they will be equivalent according to Bernoulli theory. So again, we can write this equation like P1 minus P2 equal to half into half rho v1 square minus v2 square. Again, from continuity equation, we can write v1 a1 equal to v2 a2, or v1 equal to m v2, that is m equal to area ratio between a2 by a1. Typically this is taken as a 0.5 for a standard orifice. So if you plug this into this equation, finally we get v2 square minus 1 minus m square rho by 2 equal to p1 minus p2, or v2 equal to root over 2 p1 minus p2 divided by rho into 1 minus m square, or q, that is flow rate, equal to p2 a2, that is equal to a2 root over 2 into p minus p2 by rho into 1 m square. That means if you know the area ratio and if you measure the pressure drops, then obviously we will be able to find out what is the flow rate. However, the whatever area A2 at the orifice plate, okay, when there is a flow through the orifice plate, the actual area of orifice plate, let's say A2, but when there is a flow will be contracted little bit. It can, the area through which there will be a flow will be little bit of contracted. The actual area through which the air is flowing, it will be not the A2 but some lesser than A2, and we bring a factor, okay, which is called C. This is coefficient of contraction, to calculate the actual area through which flow is going. So we can plug into the equation. So your Q will be C A2 square root of 2 P1 minus P2 by rho 1 minus C square and M square. Even though this is the actual quantity, we should get it if I know the C, M, all those things, but quantity is what is flowed through this will be somewhat less, because whatever the pressure across this, the orifice P1, P2, that is, there will be some other factor due to the shock losses, because there is a from when extra shock losses will be occurred. So total pressure drops. To account for this, we can put another factor, that is C K A2 root over 2 P1 minus P2 by rho 1 minus C square M square, or CA2 root over 2 P1 minus P2 divided by rho into 1 minus C square by M square. Even then, the actual quantity, what I could get it from here, it's differ from the this theoretical quantity, and to account for this we bring another factor k into the equation. Thus the quantity now becomes ck a2 root over 2 p minus p2 divided by rho into 1 minus c square m square. Combining this factor c and k, we get another factor, alpha, which is called coefficient of discharge. The q become then q equal to alpha a2 root over 2 p1 minus p2 by rho 1 minus m square. So if somebody knows coefficient of discharge, and then if he measure the delta P across this orifice plate, obviously he will be able to find out what is the quantity flowing through the duct or pipe. So now question is what is the value of alpha 2? So for this, to finding out this alpha 2, we need to calibrate the orifice plate. So our task is to how to find out the alpha value to the experiment, to find out what is the coefficient discharge of that particular orifice plate. For this purpose, what we can do, we can do the experiment, and we can measure the delta P across the orifice plate, and from this we can, and taking the dimensions of your orifice plate and the area ratio and density, all those things, we can find it out. A2 to P1 minus P2 by rho into 1 minus m square. And then if I somehow measure this quantity which is flowing through the duct, and this quantity Q versus this, if we plot, we do if we control, if we change the pressure drop through a throttling device by changing the resistance, if we take a number of measurement, obviously the slope will give us the what is the alpha value. Okay, so let us conduct some experiment and see how actually we can calibrate this orifice plate. Here is our setup for conducting this experiment. You can see that there is a orifice plate which is put inside the duct, and this plate is basically like a disc, and inside that disc there is a orifice, and this is put into this duct, and if we want to measure what is the quantity flow through this duct using this plate, there is a connection here. One of the pipe just take one of the tube, take the measurement just before the orifice plate. Another tube connected here just take the pressure after the orifice plate. So if I join this tube across a differential pressure calculator, then we will find out what is the pressure drop over here. Now from this we can find out the pressure drop across the orifice plate, and the dimension, this dimension of the duct we can take it, and obviously if I know the dimension of this duct, the dimension of the orifice plate will be, for this case, will be half of that. So we are get the A2 value over here, and from this we will get the pressure drop. Now if you come and do the quantity survey here using the anemometer, then we can find out what is the velocity of air which is right through the duct. And if I take this dimension of this duct at the outlet, the area, and if you multiply that, we will get the quantity Q. So the quantity Q, I get it here, and then the orifice plate sections we will get the pressure drops and the dimension A2, and you can take the rho value, that is density area, the standard is 1.12 kg per meter cube. So once I get those value, and if I measure the pressure and the quantity, we will get the Q and delta P by doing a set of experiment, like by changing the condition of flow quantity and the pressure across this by a set of measurement condition you can create by using a throttling device, throttling the air. So we will get a set of values of quantity. Now we got the value of A2. Now the pressure drop P1 minus Q2 across the orifice plate, and also we know the rho is 1.12 kg per meter cube and m equal to 0.5. Now this value we are plotting against the whatever quantity we measure, so we get a point here. Now next steps what we will do, we throttle the at the input so that quantity will change. So another new condition will be created. So we will measure the again delta P, again quantity. So we will get another point. So by doing this a set of experimental condition, creating a set of experimental condition, we will get a number of points, and now base fit line through this number of points will give you the from this base fit line, if we find out the slope, that slope is nothing but the coefficient of discharge. So once I get this coefficient of discharge, and then obviously this instrument is calibrated. Now let us take certain measurement. Here across the orifice plate, we got the pressure drop as 113 Pascal, and let us see the readings of the traversing. Now at the outlet we are doing the continuous traversing, so that velocity at the outlet we can get it. So he is doing the continuous traversing. The value we got it here 1.52 meter per second. Now this value, if you multiply it by the duct area, duct dimension, duct diameter, we got it 1.5 centimeter. So once we get this, multiply this dimension, we can get the what is the quantity. So we get the quantity from this, and then therefore we got the pressure. So we get a point in the our graph. So we will create another new experimental condition by using a throttling device, so that pressure and quantity will change. So let us get another experimental condition. We will put a throttling device to change the quantity, and accordingly also we can note the what is the pressure drop also across the orifice plate. Let us change the create another experimental condition. Now this is a throttling device. We are putting here to control the flow. Also you put this experimental another flow control will change, so our experimental condition will change. And now let us take another set of reading, both pressure drop across the orifice plate and flow quantity flowing through the duct. With this new condition, pressure drop coming out to be 39.7 Pascal. So corresponding that pressure drop, we are also finding out what is the flow quantity at the outlet, and we are also doing a continuous tower sinks at the outlet. Now let us see what is the value it's come. So the reading is coming out to be 1.46 meter per second. So now we get another point in the graph. Similarly, by changing a set of new experimental condition, we will get n number of points. Now if you fit a base speed line, slope of that line will give you the alpha value.